Okay, so this is the example we reached to last time, which is 4x double dot plus 2000x equal to f of t. F of t is given by a pulse, which is constant, then we have negative rise, then 0. So there are 3 intervals. Okay, and accordingly, the solution also has to be obtained for each interval. Okay, so the force will be a constant, as mentioned here. Okay, constant, which is F1, then F2, then F3, and you can obtain, this is the procedure. F1 is 100, and it's valid for t less than 0.1, less than or equal, and then F1 plus F2 for the second interval. Okay, so for t greater than 0.1, less than or equal to 0.2. F1 plus F2, and then you can find F2 from here, and then for t greater than 0.2, F1 plus F2 plus F3 equal to 0, and we can find F3. If you look at F1, F1 is a constant, and directly we take the solution of the constant, okay, which is x equal to F naught over k, 1 minus cosine omega nt. And F2 is a rise with negative slope. Okay, so we use the solution of the rise starting at 0.1. Okay, so it is minus F naught over k, t minus t1 over t1 minus sine omega nt minus t1 over omega nt1. We have minus 100. So this is the whole thing is minus 100. Okay, with the minus. So minus 100 over 2000 minus 0.05. And t minus t1 is 0.1 over 0.1 minus sine 22.36 t minus 0.1 over 2.236. And for the F3, okay, so this is a response due to the constant, which is F1, and this is for the RAM, which is F2, and then we have for F3. Again, we put it in this form, F naught over kt minus t1, and we find it equal to 200 over 0.2 t minus 0.2. Okay, so x is F naught over kt minus t2 over t2 minus sine omega nt minus t2 over omega nt2. So this equation, if naught is 200, 200 over 2000 is 0.1, t minus 0.2 over 0.2, minus sine 22.36, t minus 0.2 over 4.47. Okay, and this is equation number 3. The actual response, okay, is for t less than or equal to 0.1, we have x equal to x1 only, the first equation. For, okay, so x equal to x1. Like we did this last time. Yeah, we call this x1. Okay, and then we call this x2, and we call this x3. Okay, so for adding equation 1 and equation 2, which means that x equal to x1 plus x2, and then substituting for x1 and x2, we can simplify, and this is the solution. And valid for t between 0.1 and 0.2. For t greater than 0.2, x will be x1 plus x2 plus x3, and simplifying, we get the final equation for the t greater than 0.2. So in summary, x is given as x1 for t less than or equal to 0.1 equal to x1 plus x2 for t greater than 0.1 less than or equal to 0.2, and x1 plus x2 plus x3 for t greater than 0.2. So you can see that this is the way we obtained f1, f2, and f3. Okay, so this is f1. This is f1 plus f2. This is f1 plus f2 plus f3 for the third interval. So the same thing we do for the response. Okay, example, the last example I think in this chapter. This is the last one. Okay, we have a differential equation given by 0.5 x double dot plus 8 pi square x equal to f of t, where we have zero initial conditions and f of t is a triangular pulse. Given as shown in the figure. So it is a rise and then negative rise, then zero. Again, there are three intervals. So we have 0 here, this is T1, and this is T2. So F can be given as the equation of this line, which we can call it F1, which is equal to 100. Equation of a straight line is 0.2 times T, and this is valid for T less than or equal to 0.2. And then the equation for this is the equation of a straight line again. So it is going to be the slope, which is minus 100 divided by 0.2 times t minus 0.2. I'm directly substituting in the equation of a straight line. And you can simplify this equation, but this is valid for t greater than 0.2 less than or equal to 0.4, and then 0 for t greater than 0.4. This is the force. So first of all, omega n is square root of k over m. K here is 8 pi. This is k, and this is m. Okay, 8 pi square. So omega n square root of 8 pi square over 0.5 is 4 pi radian per second. The triangular pulse, okay, this is simplified here, is defined as 100 t over 0.2 for t less than 0.2 or equal. You can put the equality here. And the equation is simplified to minus 500 t plus 200 for t greater than 0.20 less than 0.4 and 0 for t greater than 0.4. Okay, the triangular pulse can be considered to be the sum of three ramp functions as shown below. Okay, so here is the rectangle, the triangular pulse is repeated, adding here f1 is equal to 100 over 0.2 times t, and this is f2, and the way, so you can say for t less than or equal to 0.2, f1 equal to 100 over 0.2 times t. For t greater than 0.2 less than or equal to 0.4, we have f1 plus f2 should equal to minus 500, the given here, huh? Minus 500 t plus 200. And from here you can find f2, which is given by this minus 200 over 0.2 t minus 0.2. And for t greater than 0.4, we should use, this is f3, f1 plus f2 plus f3 should equal to 0, and then you can find f3 from here, which is equal to 500 becomes 200 over, you have to make it in this form, huh? 0 if not over T1 minus T minus 0.4. Okay, the reason we make it in this form, if not over T1 times T minus T1, is to make it ready to find the response. So this is all RAM. Okay, then you find x1 due to f1. You find x2 due to f2, and you find x3 due to f3, and then the actual response will be given by interval for t less than or equal to 0.2. We have x equal to x1. Okay, you need to continue this. Huh? And for t greater than 0.2 less than or equal to 0.4, x will equal to x1 plus x2. And for t greater than 0.4, x will equal to x1 plus x2 plus x3. Okay, so those intervals, or x is given as piecewise continuous. Okay, you substitute and simplify. Okay, and this is the end of the chapter. Okay, this example, I didn't finish it and complete all the steps. This is all the steps, but I didn't find all the equations. So what you need is try to complete the question. Okay, any questions?
No.
Okay, so we can move to the last thing we have is the tutorial. Okay, tutorial 9. I will skip any problem that has that involves integration, so you can skip this. Question number 1, and skip question number 2, and you can skip question number 4, number 3. Okay, and you can start solving. Okay, so we will focus on constant and rise only in this chapter. Okay, that's basic things, and once you understand the problem or the types of those problems, then you can extend to any other type of excitation. Okay, question number 4, determine the response of a spring mass system excited by the force shown in the figure below. The system is initially at rest with the following parameters: m equal to 2 kg and k equal to 250 Newton per meter. So it is a undamped. All the problems in this chapter will be for undamped system. And subjected to rise or a constant, that pulses that contains rise or constant. Here we have rise and then constant, then negative rise. So what you need to do is this pulse, you have to write it as, this is a rise, and you call it F1, plus a negative rise at 0.25, and you can call it F2, and a negative rise at 0.5, you can call it F3, plus a positive rise at 0.75. Then you need to find, this is all of them are rise functions. We have 4. Then you can find x1, x2, x3, x4 due to f1, f2, f3, and f4. And then you find the actual response. Okay, so you can do this also here. This will be F1, and this will be F2 here, and this will be F2, F3, and this will be F4. Okay, the first thing you have to do is write f of t. If this is not given, you write it as a piecewise continuous function. So we have f of t is a rise from 0 to 0.25. So this is 1 over the slope times t, and this is valid for t less than or equal to 0.25. And then the equation, then it is 1 for t greater than 0.25 less than or equal to 0.5. And then the third interval, we get the slope, which is minus 1 over 0.25 times t minus 0.5, okay, plus 1. And this is valid for t greater than 0.5, less than or equal to 0.75. And then 0 for t greater than 0.75. Okay, so first thing you will do is f1 is 1 over 0.25 t. So you know that this is f naught over t1 times t. So you can use the response of the rise, okay? And f2, f1 plus f2 should equal to 1 between, okay, I will add time for t less than or equal to 0.25. This is for t greater than 0.5 less than 0.5. And from here we find f2. Okay, which is equal to 1 minus 1 over 0.25 times t, and then you take minus 1 over 0.25 common. This will be t minus 0.25, which is in the form of minus f naught over t1, t minus t1, and you can find the solution to that. Okay, for t greater than 0.5 less than or equal to 0.75, we have f1 plus f2 plus f3 equal to the third equation of f, which is minus 1 over 0.25 times t minus 0.5 plus 1. And you can find f3 from here. Okay, and then for the last interval, for t greater than 0.75, f1 plus f2 plus f3 plus f4 equal to 0. And you can find f4 from here. All of them are rise functions. The solution is the same. You can except that you need to change the value of f naught and the value of t minus t1. Okay, you can follow the example, the last example in the chapter. Okay, then you find the actual, you find x1 due to f1, you find x2 due to f2, and so on, and then you find the actual response. Okay, then you find x1 due to f2, to f1. This is okay. Find x1 due to f1. Okay, until the end. Then actual response. Okay, you find for t less than or equal to 0.25, x equal to x1. Okay, for the second interval, and so on. واضح لا؟ Okay, if there is anything that is not clear, let me know.
بالنسبة لي اوكي.
Okay, تمام. For the question number 5, We have a spelling mass system of m equal to 10 megagram, which means 10 to power 3, kilogram. We need the base unit. The base unit is kilogram. So this is 10 times 10 to power 3 kilogram. K equal to 5 meganewton per meter. It means that K equal to 5 times 10 to power 6. Newton per meter is subjected to a sudden force as shown in figure A, assuming zero initial conditions. Determine the displacement response, x of t, of the system. Hence, the force can be treated as a rise function indicated at t equal to 0, minus a rise function initiated at t equal to t1, and minus a step function initiated at t equal to t1, see figure B. Okay, here, if I would, write f of t as a piecewise continuous function, this is f of t equal to the equation of a straight line, which is f naught over t1 times t. Okay, let me move this to the right. Okay, so it is f naught over t1 times t for t less than or equal to t1. And then 0 for t greater than t1. Okay, now notice all the rise function should start from a given t, but the beginning value is 0 in order to use the response we obtained for the rise. So this function, if you call this as f1, to make this equal to 0, that means it is f2 here. And this is the negative rise, but not starting, it is starting at time t equal to t1, but its value is not 0 at t1. So it means there is a step here. This f2 equal to minus f naught over t1 times t, but this is not of the standard rise form, rise function. Okay, the form of it is not the standard. This is in fact in addition to a step. So you have to bring this upward to here and a step. Okay, so you can call this is F2 and this is F3, or F21 and F22, which means that F2 is equal to the rise is minus F naught over T1, T minus T1. So if T equal to T1, this will be 0 minus F naught. Okay, if you expand, you will see it is minus F naught over T1 times T. So F2 is made as two functions. So this is equal to F21 plus F22, which is rise, negative rise, and this is a step. Okay, you have to make it in terms of F naught over T1, T minus T1 in order to use the solution of the rise if it is starting at T not equal to 0. Okay, so this is starting at T1. Okay, so let me put it here. So you cancel this and use F21 plus F22. Okay. And then the solution you will find is due to F1, and then due to F21, and due to F22. Okay, so X1 due to F1, which is F1 is a rise starting at t equal to 0. So X1 becomes F naught over K T over T1 minus sine omega nt over omega nt1. Okay, and then you can substitute. X2 due to, let's say X21 due to F21, which is rise starting at t equal to T1. So it will be X2, it is minus negative rise, so it is minus F naught over K T minus T1 over T1 minus sine omega n T minus T1 divided by omega n T1. Okay, and you can simplify or substitute to, and then this is X21, and then you find X22, which is due to F22, which is step starting at t equal to T1. So X22 is, this is also a negative step, and this minus F naught over K 1 minus cosine omega n t minus T1. Okay, let me show you the formula, the formula sheet. Okay, sharing screen. Okay, this is the formula sheet. 2 pages, as you know. The second page is for the force vibration. And here is, this is including chapter 2, chapter 3, chapter 4, and that's it. Okay, here, the transient response. Okay, this is the transient response. We have mentioned here that we have h of t is given, but this is what we need. This is the response due to a step starting at 0, and this is the response due to a rise starting at 0. And then you can use those two equations if the step or the rise is starting at a different time than t equal to 0. Okay, so you have to do the changes, which is changing t to t minus t1 and changing f naught maybe to minus f naught. Okay, once you put the force in the standard form of rise or standard form of a constant. Okay, so those two are, we use those two, okay, in solving this in the question. Okay, so here usually this equation is same. Here we did the modification because we have minus f naught and starting at t1, so this is t minus t1. Wherever there is t, you will change it to t minus t1. Okay, the whole thing is the argument of sine. Okay, the same thing here. The whole thing is the argument of cosine. And if you want to evaluate the value, the response, and if suppose the question is find the value at t equal to 0.2, then the argument of you have to change the mode of the calculator to radian. Okay, or you make convergent from radian to degrees. Okay, so this is the response due to the forced, and then we have actual response. Is given by intervals for t less than or equal to t1, x equal to x1, and for t greater than t1, x equal to x1 plus x21 plus x22. Okay, you substitute here and you substitute here to get the final. Okay, question number 6. The differential equation of motion of undamped system is given by 2x double dot plus 100x equal f of t. If f of t is as shown below, find the response of the system using exact method, which is the convolution integral. Not it's not a numerical method. I use the convolution integral with 0 initial conditions. So we have x at 0 equal to x dot at 0 equal to 0. Here we have steps. There is no rise. So this is f1, and then we have f2. Okay, let me first of all write f of t as a piecewise continuous, which is 100 for t less than or equal to 0.1, and it is 50 for t greater than 0.1 less than or equal to 0.2, and then 0 for t greater than 0.2. So you can say this is f1 and then f2 and then f3, and then you can find them for you find f1 and f2 and f3 according to the interval. So for t less than or equal to 0.1, f equal to f1 equal to 100. For t greater than 0.1, less than or equal to 0.2, f is equal to f1 plus f2 equal to 50. And then from here we can find f2. Okay, 50 minus 100 is minus 50. And then the final interval. Okay, for t greater than 0.2, we have f equal to f1 plus f2 plus f3 equal to 0. So therefore f3 equal to f1 plus f2 equal to minus. Equal to minus 50 again. Okay, but as you can see, f2 is minus 50, f3 is also minus 50, but the starting time is different. Okay, so f2 is starting at 0.1, f3 is starting at 0.2. All the equations are similar. So you have x1 is equal to f naught over k 1 minus cosine omega nt. And x2 will be minus f naught over k 1 minus cosine omega n t minus 0.1 and x3 equal to minus f naught over k 1 minus cosine omega n t minus 0.2. And then you find the actual response. Okay, x1, then x1 plus x2, then x1 plus x2 plus x3. Okay, question number 7 is the water tank shown in the figure is subjected to the periodic force as shown in figure B. Treat the system as a single degree of freedom system and find the response for t less than or equal to 0.15 seconds. Then write the equation of motion along with the initial conditions for the interval t greater than 0.15 and should be less than, for this interval is t greater than 0.15 less than or equal to 0.21. Okay, this is called periodic function. But non-harmonic. There is to get the total solution for all time, we should use Fourier series. But here the question is simplified. Is to find a solution up to t less than or equal to 0.15. And then put the equation of motion for t between 0.15 and 0.21. Okay, so the equation of motion, this is a spring mass damper system. And dam system subjected to the periodic excitation. But we can take it as a pulse since the question is to find the response up to here, then we can extract from this the rectangular pulse. Okay, and we know that the solution will be valid up to 0.15. Okay, so this will be F1. And then this will be F2. F1 is 400. F2 is minus 400. Okay, which is rectangular pulse. Okay, you will find x1 due to f1. The solution is in fact already in the notes, and you will find x2 due to f2, and then you will find the actual response. Actual response will be x1 for t less than 0.06, and x1 plus x2 for t less than or equal to 0.15. And we cannot use that solution for time greater than 0.15. The second part of the question is to put the equation of motion. Okay, so actual response it will be for t. Okay, this I will take 2 minutes. For t less than or equal to 0.06, x equal to x1. For t greater than 0.06, less than or equal to 0.15, x equal to x1 plus x2. And this is what is required in part A. Part B, okay, is to find the equation of motion. Equation of motion is mx double dot, and we have the mass is 5 or 10 megagram. So it is 10 x double dot plus 5 mega Newton per the whole thing multiplied by 10 to the power 3 equal to, for the interval between 0.15 and 0.21, we have f equal to 400. So again, you need to put here equal to 400. And initial conditions will be x equal to okay, we have x at 0.15 equal to x1 at 0.15 we obtained before, plus x2 at 0.15. And x dot at 0.15 is equal to x1 dot at 0.15 plus x2 dot at 0.15. Okay, those are the previous solution obtained from a previous solution. Okay, this is very slow. Okay, both of them. Okay, this is the required thing for this question, part B. Okay, question number 8. This is the response due to critically damaged. You can skip this question as well. Okay, as I told you, we will do only the undamped. Okay, question number 9. Find the response to the of the system 3x double dot plus 12x equal to f of t with 0 initial condition, and we have the pulse is given as a constant. So we have a constant equal to 1. This is f1, and then this is f2, and then we have f3. Okay, and then you can find f1, and you can find f2, and you can find f3, and then find the response x1, x2, x3, then find the actual response. I hope it is clear. Question number 10. The equation of motion of undamped system is 2x double dot plus 1500x equal to f of t, where the forcing function is defined by the curve below. Find the response of the system assuming 0 initial conditions. So again, this is a rise, you can call it F1, and then a negative rise, you can call it F2, and then you have F3, which is a step. Okay, this is positive rise, and this is negative rise, and this is a step. The starting time for each one is different. This is t equal to 0. Starting time is 0. The starting time is 0.1. Starting time is 0.25. Okay, and you find the response due to F1, which is a rise. You find the response due to F2, which is a negative rise. And then you find the response due to F3, which is a step. Then you will have X1, X2, X3. The actual response will be X1 for t less than 0.1, and it will be X1 plus X2 for t less than 0.25. Okay, so this will be here. And X1 plus X2 plus X3 for t greater than 0.25. And similarly, you can do this for question number 11, undamped system 2x double dot plus 150x equal f of t with 0 initial conditions. And we have f equal to all are constant. There is no rise here. So you will find f1, f2, f3, f4. Okay, this is starting here, this is starting here, this is starting here, and f1 is starting from 0. and you'll find if x1, x2, x3, x4, and then you will find the actual response. Okay, and this is the final thing in this tutorial. Okay, so Sunday we will have quiz number 4. Okay, quiz number 4 somewhere here. Okay, about tutorial 7. Okay, on Sunday. And today I will see you at 3 p.m. For the experiment. All right. Any questions?
Online low.
Yeah, online. Yeah, online. Okay, see you.